I'd like to share with you this morning some of the changes that have taken place in TESS, since many of you have heard about the mission at KASC-7 in Sydney. And we're on a very accelerated schedule, and there have been some modifications that we've been fortunate enough to make in the operation of the satellite and some of the characteristics that I'd like to describe. The team that's associated with TESS is shown in this first slide. These are veterans of the Kepler mission in many cases, as well as a small group who've had experience doing small satellites in the past. There's a mission paper on TESS that was just posted last month that has many of the items that I'll be discussing today, as well as some additional information about both the science and the technology of the mission. This is the team that's associated with TESS. There are 6 partner institutions with the responsibilities that are given in this slide, but in addition, there's a very large group of collaborators and contributors from a number of institutions worldwide, and we're inviting other participants in TESS to come forward over the next 2 years to actually join the team as well. The goals and drivers for TESS are shown in this first slide. The major focus is to find small planets orbiting bright nearby stars, and this will enable us to distinguish between rocky planets, water worlds, and ultimately, hopefully for a few instances of habitable planets. Now, in this sense, we use this word best to describe the 1,000 small planets that are associated with the mission, where by best we primarily mean that the host stars are bright, and that will immediately lead to measurable mass and atmospheric properties. And currently there's only 3 instances of such planets that are known. The survey itself will comprise a variety of dwarf stars, all of the nearby M dwarfs that we know of, and we anticipate covering the entire sky in 2 years. The question often comes up as to the differences between TESS and Kepler, and I think for TESS it's easiest to say that we're trying to find the nearest transiting rocky planets, whereas the major question that Kepler has been targeted to is the question of how common are true Earth analogs. Now, in order to answer the question the way that TESS is posed, it's important that we find bright stars. Now, there are 2 ways in which we can do this. The first way is to increase the solid angle coverage by about a factor of 400, and the number of accessible bright stars increases by that same factor. The second thing is that we search stars that are near, and in the case of TESS, we're typically reaching out to about 100 light years, whereas for Kepler that number is about a factor of 10 larger, so from 1 over r squared, that means the TESS stars should on average be about 100 times brighter. And this next slide shows the differences that this represents in terms of a plot of host star magnitude versus planet radius. And the red dots show the TESS stars that are anticipated, and the blue dots show the ones that are anticipated, the ones that are known from Kepler. And as you can see, there's a difference of about 5 magnitudes on average, so that's indeed about a factor of 100. And that means the TESS planet should be easier to follow up, which will mean that in this upper left-hand quadrant where the Earths and super-Earths are located, there's going to be a good selection for follow-up work. One of the things that we've been able to add to TESS since the mission was selected in 2013 is the capability of bringing down full-frame images with a 30-minute cadence. And the full-frame image means that we basically have 100% of the field of view, all the stars, and in the instance that I'm showing here, this represents in a 3 by 3 degree field of view about 1/3 of a percent of the instantaneous TESS field of view. So on the scale of the screen, that would correspond to the image being about 20 stories high. Now, there are the stars that would actually be covered for this by limiting magnitude are shown in this table. And as you can see, as we move down toward an I-band magnitude of 14, the number is actually in excess of 20 million stars. Now, if I plot the little yellow squares that represent the 10 by 10 postage stamps or imagettes, they would cover about 2% of the field of view. So basically what we're doing by this method is we're recovering the full 100% and the 98% that we're missing. So the bottom line is that we will be able to provide full frame images at Kepler's 30-minute cadence. This is the spectral response that TESS has. It goes quite a bit more into the red than was the case for Kepler. Basically, there's a cut-on from a filter at 600 nanometers, and then the CCD naturally falls off at about 1 micron. The peak absolute throughput then is about 80% in the range around 850 nanometers. This is a cross-section of the focal plane cameras that we're actually using. The detector assembly, the lens assembly, and the lens hood are pointed out. And the pupil diameter, the passband is about, as I said, 600 to 1,000 nanometers. And with the number of cameras that we have, we'll be able to cover about 2,300 square degrees. So it's about 20 times the field of view that Kepler has. And then this small table gives some of the temporal characteristics that the camera actually has. This gives a little bit more detail on the cameras themselves. This is a cross-section showing the lens assembly on the left and the focal plane and the electronics which are inherent to the design. The lens itself is a modified Petzval design with 7 elements, 2 of which are A-spheres, and there's a coated surface on the second lens that actually provides the cut-on filter at 600 nanometers. The CCDs for TESS we're actually fabricating at MIT at the Lincoln Laboratory. The front illuminated processing was completed in January, and we're in the process right now of doing the thinning and backside treatment. The yield has been quite good so far. Altogether, we're going to fabricate about 200 devices and select the best 16 as flight candidates. This is the design that's actually used. It's a little bit different from what the people familiar with Kepler would have seen. We're using half the silicon area as a frame store, and that means that we can quickly shift the image in about 4 milliseconds from the imaging 2K by 2K area into the storage area. Basically, when we put the 4 CCDs together in the focal plane assembly, which is shown in this slide, we then cover up half the silicon with the completed focal plane array. So there's a total of 16 megapixels that are associated with the imaging area for each of the cameras. This is what the camera prototype looks like. This is it weighs about 10 kilograms altogether, and you can see from left to right, in the lower left, that's this is Tim Sauerwein, who is our project manager. He's cradling the CCD and electronics assembly, and then his other hand is holding the lens assembly, and then the baffle is at the upper right. We also built a full-size replica for TESS. TESS is quite compact. As you can see, it's only about 1.5 meters high. It only weighs about 400 kilograms. And the structure next to Sarah Seeger is the Ka-band dish that will actually transmit the data from TESS's orbit. And Josh Wynn and Roland Vanderspek are in the picture as well. Josh is the deputy head for the TESS Science Center, and Roland Vanderspek is the deputy PI. What I'd like to do now is show you an animation of the sky mapping strategy for TESS. There's more details at this video on YouTube if you care to look at that as well. But basically the way that it operates when TESS is on orbit, The 4 cameras are arrayed so that they extend their fields of view from the ecliptic up to the ecliptic pole. Each camera covers a 24-degree square fields, and they're edge abutted, so the total extent is 96 degrees going upward. In order to provide extended coverage at the ecliptic pole, we actually take one of the cameras and center it around the pole. And then every 27 days, or 2 orbits of TESS, we shift the fields of view, and as we shift the fields of view, we cover a new piece of sky, but in addition, the continuous viewing zone at the ecliptic pole, which is the same for TESS and for Kepler, for JWST, will be viewed repeatedly. And then in the second year, we flip it over and do the alternate hemisphere. So altogether, there's a total of 26 pointings and in the coverage in the 2-year baseline mission. The coverage that we end up with after the 2-year baseline mission is shown in color on this map. The pole is indeed the ecliptic pole, and the coverage extends from 27 days up to 350 days in the continuous viewing zone at the pole. And in fact, the dashed line that's shown, the dashed circle, is the 10-degree cone that's continuously viewable for JWST. Now, in order to provide TESS with the type of coverage that we've shown in that previous video, we have to go into an unusual mission orbit. And that's what this video actually shows, is how we get into that orbit. TESS is launched initially into a highly eccentric orbit going out to 250,000 kilometers. The perigee is about 600. Then we successively adjust the apogee by perigee burns, and after 3 of these, the apogee has been raised to about 400,000 kilometers, so it's approximately the distance to the moon. In fact, it should be exactly the distance to the moon. And then we do a lunar flyby, which adjusts the inclination of the orbit to about 35 to 40 degrees, and that's what's shown here. And then there's a long excursion that lasts about 30 days, and then the satellite comes back to Earth again. And then there's a final burn, and then there's an adjustment that takes place, which provides the final orbit, which has a perigee of 17 RE and an apogee of 59 RE. And so this is the basic mission orbit that has a period of 13.7 days. Now, the reason that this orbit has been chosen is covers a number of reasons. It's a resonant orbit with the moon, 2-to-1 resonance, and in the cartoon that's shown here, this is TESS, this is the Earth, and this is the moon. And then when you look at the phasing that we've arranged, at the point that's coming up now in the animation, you see there's a 90-degree relationship between the two. And then 2 weeks later, when TESS passes through apogee again, the moon has moved half its orbital distance, its orbital track. So the net result is there is indeed this resonance, but more than that, what happens is that the moon is actually used to torque TESS's orbit in one direction for half a lunar month and the other direction for the other half of the lunar month. And so basically we end up with secular stabilization, and this orbit is actually stable with no station-keeping burns or anything of the sort that would be required at L2 for timescales of the order of decades. The other advantages of this orbit are shown in this slide. I won't read all 9 of them, but one that's particularly important for achieving the new science that we're able to bring from TESS are the high data rates. We're able, because of the fact that we come into 100,000 kilometers perigee, to use a very high data rate. So we can actually downlink about 200 gigabytes in a 3-hour dump. And that means that the 1 over r squared advantage that we have to a drift-away orbit like Kepler or Earth-Sun L2 means that we can bring down a great deal more data hence our ability to bring down full-frame images. There's more details on this special orbit in a paper that we posted on AstroPH. Well, going back to the science of why TESS, why now, as I stated at the beginning of the presentation, our goal is to look at small planets orbiting bright stars, and the three instances that we know of right now are shown in this slide. And as you can see, from sub-Neptunes going downward in size, there only were these three space-discovered candidates that were currently known. And then when you put the TESS yield planets in this, they were able to populate this plot quite nicely. So another area that's of great interest to many of us is asteroseismology, and this plot shows the log of stellar radius versus TESS or Kepler magnitude, and the information you can gather from this quite quickly is that the Kepler objects are fainter, the TESS objects are larger, and if we take into account what we think will be the saturation limits that the TESS CCDs will have, that means that we can go conservatively to a factor of 100, which would mean that we would be able to bring information down for stars as bright as about magnitude 2.5, and if we can actually process and with no loss images that are streaked in the same way that the ones from Kepler were, by a factor of 1,000 saturation factor, then we should be able to basically do all the bright stars as well, even down to 0th magnitude. So this is something that we're testing this fall with the new devices that we've produced, and so I think the result may lie somewhere between these two bounds, but hopefully closer to a factor of 10 to the third than 10 to the 2. The other thing that we've been able to do in the last year and a half is to provide for some additional capabilities in timing that will benefit asteroseismology. The noise floor for TESS has been set conservatively in the level 1 requirement at 60 parts per million per root hour. However, the properties of the orbit and the satellite and the instruments are such that we should be able to achieve better than 10 parts per million. The formal number is 7 parts per million currently, and that means that we should be we should have fewer limits than we had thought originally. Now there is also a possibility that we'll be able to put in a special asteroseismology cadence for a few thousand stars. 30 seconds, 45 seconds seem to be readily achievable. And depending on the data compression, we may be able to reduce the full frame cadence time from 30 minutes to 20 minutes, and that's something that we're hoping we'll be able to do as well. One of the things that has resulted in our ability to improve the timing is there's a chip scale atomic clock that has been developed over the past decade by DARPA. It's now been flown on the space station, and we would use this as a phase reference for the spacecraft clock. This unit, which you can see compared to a U.S. quarter, which is about the same size as a euro, it's very compact. The mass is just a few grams, and altogether the power is only about 100 milliwatts. So this is a very attractive secondary reference that we would just use to phase track the master clock in the satellite. And we can relate this to UTC by comparing to ground-based observations of bright eclipsing binaries. These are the yields that we're anticipating for TESS in the 2-year mission. The bars in red are the ones that we've talked about previously from the postage stamps. Adding the full-frame images increases the number of large planets that we anticipate by quite a large factor. I mean, note that this is a log scale, so the numbers for the sub-Neptunes and giants are quite large. for small planet validation and mass measurements, there are commitments in the mission that are shown by the names of the telescopes on the left, and the flow down is shown in the right in this funnel that describes how we go from light curves for the 200,000 postage stamp stars as we go down. And the team itself is committed to establishing 50 measured masses, but the actual number of candidates that we're likely to have that will be available to the community. In fact, all of the data is available to the community after 4 months, but there's 2 or 3 times as many likely candidates that will come out from this. So the data will be delivered to the MAST archive in 4 months' time for the entire community. One of the things that's going to be a limitation in this process, which everyone who's worked on CoRoT and Kepler is aware of, is the limitations in the numbers and availability of precision radio velocity spectrographs. So this situation is hopefully going to improve in the next few years, and these are some of the facilities that we're all hoping will come online in time to help TESS, Cheops, and ultimately Plato as well. For TESS in the habitable zone, this is a nice diagram that Sarah Seeger put together for an article in Science last year that shows the radius of the orbits relative to Earth for stars and systems of various masses on the left, and the region that TESS would actually explore is shown in this red rectangle. The way that this habitable zone is accessible to TESS is easy to see in this plot. This is orbital period versus stellar temperature. So spectral classes of the dwarfs that are accessible to TESS are shown along here. And the red trace shows the line that you expect the locus for the inner habitable zone, defined arbitrarily as twice the solar insolation, and the outer habitable zone as half the solar insolation. So for the 27-day portion of the sort of what we could call the all-sky survey for TESS, these are the regions that would actually be covered with the percentage of those systems shown at the bottom. And then for the area near the ecliptic poles, this is the coverage that we would actually have. So basically for the ecliptic poles, we'll be able to go all the way up to solar-type stars. This is another way of viewing that information for small planets, less than 2 Earth radii. So the dashed line and the dotted lines show a couple of different models that are actually somewhat broader than the range that we chose here. But as you can see, there's about a dozen habitable zone planets that we expect to have that are in this radius range. These are the yields that we anticipate having for TESS as a function of eye magnitude. And as you can see, there's going to be quite a few that will be in the range of 8th to 11th magnitude. They're going to be prime candidates. And then when you transform the actual planet numbers by K magnitude, which is a natural passband to use for JWST, the numbers that you get are the ones shown in this plot on the right. So to summarize, the yields that we expect from TESS are shown in this table. There should be about 100 small planets that are going to be in JWST's continuous viewing zone, and a handful of those will be Earth-sized planets. And so in 2 years, we anticipate that TESS will discover the numbers of planets that are shown here, and all of these are orbiting bright stars. And then finally, this is the summary of the key points for the mission itself. And if someone asks a question, I can tell you about something we thought about for a follow-on to TESS as well. Thank you.
Time for questions. Yes.
From the detection yield, it appears that you define the detection as detecting 2 transit events over a particular planet.
That's right.
That in the presence of multiple small planets, that's kind of tricky to have to distinguish between two events and say that they are attributed to the same planet and not to two different planets and so on?
Well, I think that's a problem that's been handled quite well by the Kepler pipeline, and I'd just point out that, that the group at Ames that's been responsible for that effort is also going to be responsible for the work on TESS, and the ability to utilize information that's present in, certainly in the high signal noise detections in terms of the profile of the transit itself is something that we'll utilize quite heavily.
Yes.
So has it been decided which hemisphere you observe first?
It hasn't been firmly decided. There are pros and cons to either one. One factor that may come into play is because of the way that we get into this orbit, whether we launch into the ascending node or the descending node could make one or the other of the two hemispheres more attractive. And then, of course, the major scientific reason will be the follow-up capabilities that are available for precision radio velocity in the first year versus the second year of the mission. This is something that we're going to have to decide about a year before launch.
Yes, you
Hi, George. I have a question. Would it, finding astroseismic targets for short cadence, for example, things like white dwarfs,
Right.
is very difficult from the ground. Would it be possible in the continuous viewing zone to take some full-frame images at fast cadence, even for only an hour or two, give people on the ground time to analyze them and find the candidate pulsating stars, which could then be put into postage stamps in short cadence later on?
That is something that the flight software would likely be able to do. The system is being designed so that you can basically put 3 masks down in the processing that's done in the FPGAs in the front end of the data handling unit. And those masks, one of those masks is nominally for full frame images, one is for the 1 or 2 minute cadence, and then the other one would be used for both guide stars and for the special asteroseismology cadence. Since those buffers are the same size for all 3 categories, we could, in principle, utilize one of them for a mode like that you're describing. So one of the things that I didn't mention that it would be really great is that there are a number of working groups associated with TESS. This is not just the CoI team, and ideas like the one you're suggesting would be welcome, and that's exactly the kind of planning that we're trying to do in the next year.
Since we're at the KASC-CoRoT workshop, I thought we should say that we are now establishing also the TESS Asteroseismic Science Consortium, the TASC, which is very much going to be based on the KASC, and we certainly look forward to collaborating with the team. The whole organization is going to be established during the next few months, and so next year's KASC workshop is really going to be a KASC-TASC workshop. Right. We certainly look forward to that.
Yeah, I'd add to that there also are going to be working groups established for non-exoplanet, non-asteroseismology group. For example, a number of people have expressed interest in utilizing full-frame images for purposes that have little to do with stellar or planetary astronomy. Gamma ray burst afterglows, dwarf afterglows, AGNs, tidal disruption events. A lot of ideas have been brought up for utilizing the data for that purpose as well.
I think I'm sorry, but we are limited with the time. So thank again, George.
You're welcome.